All right, team. We're nearing the game over stage, all right? Very close. Okay, so I have a bunch of things to tell you about. Well, we have this exam thing right on Monday, so that's an issue. So we're going to talk about that. We have the last assignment, number 10, Tetris, is due on Thursday, which is not here, right? So you'll have to come by my office at Farrell Hall, which is the Triangle building, if you haven't been to it, at the back of the Trinity campus. I'll say that again, it's on the web. We're going to talk a little bit today about SVD. We're going to just give you a couple more examples. Yes? What hours are you going to be there? Yeah, so I'll show you some stuff on the board, the thing here in a second. Yep, sorry. So I'll finish, there was a calculation we did the other day, and I'll show you the pictures that go with it. We haven't done that. I'll give you another one, maybe a couple of others. We'll see how we're doing for time. And your excitement level, I know, is always high. We'll talk, and then I'll give you a couple of examples of SVD, which is used in a lot, many places, right? But I'll give you a couple of fun ones. So for Google, right? So search. We'll use it for search, informational networks. And then something quite different, image compression. I'll give you the Scottish fabric guessing game. And then, yeah, game over. So, yeah, we'll have a fun, some crazy things. So I spent last night putting Perl scripts inside of LaTeX, inside of Perl. So, you know, sort of a turducken. But like a turduckirky, with a turkey inside a duck inside a turkey. Yeah, anyway, so if you like LaTeX, I'm happy to talk about these things. Okay, all right. You can ignore that. That was craziness. Okay, so let's see. So that's where we're going to go. And I'm going to show you some things that are online. If I can keep myself together. So let's see. I know it gets emotional in the last lecture. So, you know, just... Yeah. And this building is going to be knocked down, right? So it kind of is for the building's point of view. I just tweeted that whiteboards are the AstroTurf of education. So it's a shame to see this stuff go away. Okay, so I've generally been putting these little notes at the top of the front page of the website, right? So let's see. So no office, we've done that. We're going to have office hours 12:30 to 3 on Wednesday. So the final, and so you can come and talk about the final assignment, which covers positive definite matrices and SVD, and there will be two questions about those on the final exam, which covers everything. Okay, so then you can hand in that assignment that day, of course, you can hand it in, that's fine, but the time to hand in is by 1 p.m., again at my office, Farrell Hall, on the Thursday, and then we'll have bonus office hours 12 to 2 on Friday. Okay? We good? What else does it say? Yes, and then we have to come back here at 1:30 for a final boss level on Monday, which I believe I have correct. Okay, so all right, so everything's graded up to level 9 and the third exam, and for most of you, I have 3 pieces to hand back. So come by any of those times, and I will have the objects on display with solutions, right? So come by and pick all those things up. I could have brought them today, but it would have been mayhem. Okay, so you have to come at least one of those times. Let's see, you can look at grades again, that's the usual business. Level 9, we kind of a little spread on that one, so team took a bit of a hit there. Kind of got smoothed out a little. Okay, so I realize we're getting to the end of the semester and you know, the team is struggling a little bit. There will be, as usual, I'm going to give you these, right, all these things are here. We're going to talk about this stuff today, singular value decomposition, so you can play around with the slides later on, they'll be there. There is an important set of slides here, which is, and maybe I'll print these out for you, but I'll show you these later on. It's just 2 pages. Okay, madness. Let's see. Oh yeah, you have to tell people what you think of the course. And let's see how we're doing now. Did I reload that? 124D, D for just the best, obviously. So we've got 46 out of 71, that's pretty good. But we are behind, horribly, we're behind another 124 thing. Anyway, so if you have horrible things to say, don't say it. Is all I can. No, you do whatever you want. Do whatever you want, it's fine. But if you have not entered your thoughts, please do that. All right. There is a page I was going to mention that's it's linked to on the website. And you can kind of sit here and think about all matrices that we've played around with. You've looked at a lot of these. And so there's a zoo here for you, right? A taxonomy, a zoo. Let's call it a zoo. We've talked about these: real positive definite, real positive semi-definite, right? Real symmetric, these things, diagonal. So they're all in this big box. And these are where they're subsets of other types. And so you can see there are all these other things that are complex matrices and so on. There's a generalization of real symmetric to Hermitian matrices. We're not going to talk about it. It's all there. There's madness over here. Anyway, there's a whole, that's a sort of a thing to come back to if you find yourself running around with matrices in the future, which I hope is true for you. All right, let's see. So that's most of the things that we had there. All right. Okay, so we're going to do a little bit on the board. Not going to hurt ourselves too much. We've done a lot of that, and I'm going to do that. All right, I'll put this up. You like this up, right? Okay. So let's do some righty things. I'm going to solve, just finish what we did for this one example. We're going to solve another 2 by 2, and then I'll kind of go backwards for a 3 by 2 or something like that. All right? Okay. So the plan is 3 SVD examples. We okay? This sad? What's wrong with those little beasts? I feel like, is that one dead? Let's get this little thing up. All right. So it's blinking, it's dying. Well, if one works, that's why we have this whole, look at you, you stupid thing. Oh, we try so hard. Oh. Stupid robots. Okay, all right. Okay, there's a bad robot joke, but I'm not going to make it. Okay, all right, so let's see. So we have, actually it's pretty good. Let's see, so we have this thing. So we did this. We had A, this innocuous little character here. It was just 1/5, 2, 11, 10, and 5. Let's do it. So this is from last time, previously in Matrixology. So from last time, we went through this calculation and we showed that we could write, and we sort of derived this whole business that we can write these things as U, sigma, let's talk about these things again, V transpose. This is, let's get this stuff, M by M. This is an M by N. This is the kind of the guts of A sitting here. And this is an N by N. So in here is an orthonormal basis. And we'll have a nice summary for it, so you don't have to write too much. Orthonormal basis for row space is in the columns here. And this is an orthonormal basis. It's pretty magical, right? I know you think magic when you think about this class, but it really is true. Matrices do these strange things. Orthonormal basis for column space. And this little beast in here looks like this: sigma 1, sigma 2, down to sigma r, where r is rank, 0 is everywhere else. R equals rank. And we had this thing we can say that sigma 1 is greater than or equal to sigma 2, is greater than, so we can order it. That's going to come back when we look at sigma r, and then sigma r plus 1 equals 0, or let's say sigma I equals 0 for I greater than or equal to r plus 1. So, right, let's do it. So we showed that this works. It was all from diagonalization. It was all from symmetric matrices. It's a spectacular thing. And let's see, we have everything here. So, okay, so it ended up like this. Yes, 1 over root 2. So I just want to write this down. Is where we got to. 1, 1, 1 minus 1. So this in here, along with this factor, is U1. And this is U2. These are the vectors that describe row space. For row space, I should say, sorry, it should be row space and everything is there, yeah. So, and null space. Getting carried away. And this is for column space and left null space. The great left null space. We're just going to do it. Let's beat it out. Okay, there's going to be this. Here's the guts of the thing in here. It was 2 root 2, 0, 0, and then a root 2. So this is our sigma 1. This is true for every matrix. And you're thinking that is awesome. I know you are. And then we have 1/5. And this is a transpose matrix, -4, 3. And so this piece here, again with that factor, and this piece, this is V1 transpose, this is V2 hat transpose. This is what we got to. So we unpacked it, we showed it's this thing, right? And you can do diagonalization with normal eigenvector approaches, but there's something different about this. There's something special about this. Right, so I'll just put it here, compare with. Can I do that? A equals, in general, S lambda S to the -1, and potentially A equals Q lambda Q transpose, if A equals A transpose. So what we gave up, we really like the orthogonality about this. We really like the diagonalization part of this, but we can't get that all the time because, for a start, we can have n by n. It can be rectangular, so that all fails. And we really needed, it's not always true, but generally we need this nice symmetry story to get this business. Okay, so we get something like that. We get orthonormal bases for Rn, I should say, and Rm, and we get this nice simple matrix in the middle. So let's write down, so what I'm going to try to do is write down exactly how this is working, use sigma v transpose for this particular example. Let's draw pictures. So how y equals ax works. Yeah, let's do it. Okay, so we have A equals U sigma, which is fun to draw, and then we have V transpose. Okay, so what do they do? What do they do? So this one, this does, so this stretch, right? All of these things are greater than 0, so stretches or shrinks vectors and sends them from Rn, this is always confusing, I know, from Rn to Rm. This is a basis transformation. This doesn't do anything. This is just a basis transformation. So all the work is in the middle, and it sends natural basis in, let's do it, this is great, this is fantastic, we'll have some fun things, in Rn to the V basis. And then this one is another basis transformation, and it brings you back basis transformation, so it's the U basis to natural basis in Rm in general. This is in general. Let me draw some pictures then for this little beast. Okay, good. I'm going to use all of this. So we have, for a start, we have this. We're in Rn over here. This is Rn equals R squared, which is where, in general, X lives. Right? This is our big picture story again. And so we start, because we like this whole Descartes thing, not the duality of mind, and that's silly, but this part is good. I hat, J hat, right? We've got that business, so I'll write it as 1, 0, and 0, 1. That's our natural basis. That's where we refer to everything in this basis. Okay, so what's U doing here? Sorry, what's V doing here? V transforms it into this new basis, which is 1/5, 3, 4, and 1/5 minus 4, 3. So let me try to draw them. I want to use a different color. So it's a circle story. That's important. It's always a circle to start with, or a sphere. How's that for us? Okay. Right, so if we're in 3 dimensions, it's a sphere. If we're in 23 dimensions, it's a 23-dimensional sphere-y thing. we're going to rotate around to a new orthogonal basis. So this is at right angles. This is V. If I go right, V1 equals a fifth, 4, 3. And this is V2 equals 1/5 minus 3, 4. So instead of expressing, so we've got this is our x. X is going to be now in terms of this basis instead of this one. Right? So instead of saying it's something times 1, 0 plus something times 0, 1, we say it's something times V1 plus something times V2. That's what V does, right? So, so V transpose X gives X in the V basis, the V hat basis. Doesn't change X, right? It doesn't change X. Does not change X. It's still the same point. Exciting, very exciting for you. Okay, okay? And then we do the work, right? So now it's broken into these pieces that A really is built out of, and it really likes these vectors. And V1, it's going to multiply by 2 root 2. And V2, anything in the direction of V2 is going to multiply by root 2. It knows how to deal with them. And then we have this whole business of where they're going to end up as well. So let's draw over here. We're going to again have a, wow, straight lines, people. Okay. Would fail various tests. Okay, all right. Let's see, so U1 and U2. So they are very simple. It's 1, 1, and 1 minus 1. So let's draw those in. We'll draw a circle again. Circles are fun. You know, there are world championships, right, for drawing circles? Yeah? You seen this business? People get, they're like, they, whoop, and they're, look it up on YouTube. It's kind of amazing. Amazing in various ways. Okay, so, all right, so here we are. This is, let's draw in U1. Now it's changed a bit actually. This is U1. Normally we kind of like going this way, right? That's sort of our default structure for, right? If we had a third dimension, we'd do this. In physics, we'd do things with our right hand because we're hanging on to the whole left is evil thing. Sinistra, very bad. Okay, U2. That's where they are, right? So this is 1 over root 2, 1 minus 1, yep. And this is 1 over root 2, 1, 1. So we're getting the mechanics of A laid bare. So excited. It's really good. It's worth a different color. All right. So V1, anything that's pointing in the direction of V1 is going to end up pointing in the direction of U1. And there's going to be a 2 root 2. So 2 root 2, 2.8 something, right? So let's put it out here. So it's going to stretch anything in the direction of, right? So this is 2 root 2 U1 out here. If it was pointing in the negative direction, it would also stretch it. So we're going to work with this sort of basic, what happens to any point on the unit circle. So what happens to x on the unit circle? Right? Right. So let's think about that vector. It gets sent to U1 and gets stretched. This is what it says. It says take, if you've got a U1 vector, it comes to here, gets multiplied by 2 root 2, and then this says change it into a basis where we think it is now actually pointing in the direction of 1, 1 here. So this character, this one here is A times U1 equals sigma 1 times, sorry, A times V1 equals sigma 1 times U1. That's our basic, right? We have VI and sigma I and UI. That's our first one. It gets sent over to there. So it's 2 root 2 times U1. This point here would get sent to here. Right, so this would be A times minus V1 hat equals minus, well, let's make it sigma 1 times minus U1. What happens to this one and this direction? Right, this one goes flying over to, I'm going to put it about here. Yep. green. Okay, and that is, so this is root 2 times u2. Ha. And so this multiplication is a times v2 equals root 2, well, sigma 2 times u2. And this is root 2. This is 2 root 2. All right? This one will get sent to here and stretched a little bit as well. So this is going to end up here. Let's draw it. So this will be minus root 2 u2 hat. And then the whole thing, if we take, it's linear, right? So if we take all of this circle, this part is going to end up here and stretched. This part is actually going to flip and stretch a little bit. And so we're going to end up with, let me make a, I'll do a different color. Looks like a pineapple. All right. So this is unit circle maps to ellipse. So it's all about footballs and spheres and things like that. All right. Ellipsoids. Yep. What else should I say? So there's so much bound up in sigma, right? The sigma does all the work. So sigma stretches and shrinks. It depends on shrinks and this. So it does one, it does this thing, and two sends vi hat to ui hat. So that could have, so this could be rotation as well. Rotation and flipping. Right, so if you imagine this was all these points, right? This is actually a pizza full of points. Right, not just the ring here, the circle. Pizza full of points. You go over here and you go slap and stretch it this way and stretch it this way a little bit. Right, and that keeps going out all the way out. Right, so concentric circles do this. So very simply, all matrices do this in some way. Right, if it's many higher dimensions, there'll still be a bunch of v1, v2, v3. Say, and a u1, u2, u3 up to the rank. Yeah. How are we doing with that? All right, let's do one more. Let's do one other calculation. We're running out of time. What's going to be the big deal that you'll see when we get to, particularly to images is these numbers. So say we have 1,000 by 1,000. These numbers decay very quickly, these sigma values. So the first 10 might be everything. Right? They might be the really big numbers, and then you're only adding small corrections. We'll see that in a little bit. What else am I going to tell you? Okay. There is one other thing I want to show you about this. That's a big board. Let's do that. Boop. Okay. All right. Let me write one more thing for this. So just as for, A equals Q lambda Q transpose, we had this. We had lambda 1. Do you remember this business? So we had V1, I have to write my V's, V1 hat transpose plus lambda 2, V1, V2 transpose, V2 transpose. So they look like this, outer products. Remember, this is a really important thing. This is going to be a big deal when the next piece. Plus, all the way out to lambda n, Vn transpose. Again, this kind of thing. So these are all outer products. And this is only if, so no good, so not possible, if S does not equal Q, right? If we don't have an orthogonal matrix.
Are your V1 and V2 hat vectors, right? That you draw on the left-hand thing?
Oh, are they bad?
4 and 3 and then negative 2 and 4.
Oh.
Right, because the transpose is
Oh, I see what you put. Yeah, right. Did I do it right? So it should be, you're right, it should be 3, 4. Actually, I did tilt it up a bit because this should be above the, yeah. So that was correct, but my brain fried it here. Thank you. So this is 3, 4. And then this is, I hope, minus 4, 3. Yeah. Sorry. Thank you. So is that good? All right, well spotted. Brain. Okay. So such a disappointment to me. Okay. So so we did this. We can also do because of the sigma thing. We can do the same kind of magical stuff, right? So now we have this. Now for all A, we have this business. Same kind of calculation works. We have A equals sigma 1, but it's different because we have U1 and then V1 transpose. This is a really magnificent thing. Plus sigma 2, U2, V2 transpose, right? These guys are different. Plus, and it just goes to sigma R, rank, U, R, VR transpose. So again, same kind of stuff. This kind of shape. So for that example, so above example, so A equals, what is it, 1/5? You can catch me when I do the wrong things. 11, 5 equals, okay, so it's going to be, we're going to have the U's and we're going to have the sigmas. So the sigmas are, let me write them in different colors. There's a 2 root 2. That's sigma 1. And there's a root 2. That's sigma 2. It's an important thing. It's beyond your problem set. And then we have these little beasts. So we have a 1 over root 2. This is U1. And 1 over root 2, 1 minus 1. So this is U2. This is U1. Like that. That's good. And then we have these little outer product pieces. So it's going to be this one. It's a 5th. Let me get it right because I'm getting it wrong. This is 3, 4, right? Yeah, 3, 4. And there's a big plus here. And there's a 1/5. And this is a minus 4, 3. Yes, good. And this character here is V1 hat transpose. This is V2 hat transpose. So all matrices can have this, can be written like this. It doesn't matter. It's an m by n. There'll be a little vector of length m here and a row vector of length n here, and we'll lay them all out. The important thing is that these are of unit weight, right? These are unit length. So the amount they contribute, when you add all of these, you tile these pieces up, to get this is really here. So the sigmas are very clear, right? If this sigma is 5,000 and the next one is 2, you can start to neglect those other ones. And this, weather prediction, all sorts of things. People will use these approximations. We'll get to it. But these things, these are outer products. These are the pieces that look like Scottish fabric, right? These look like tartan because it's just the same column with different modulations, the same row with different modulations. So we'll see this. So these are pieces of tartan. It's really true. Scots. We're onto something. The Scots, they're great. Let's see, how are we doing? 1:30. I think I will add this example. Okay, all right. Okay, so one more example. Example 2, we're going to do this one, and I can sort of jump through it a little bit, I guess. So it's a funny looking one, 3 minus 1, 3 minus 1. It's a 2 by 2. But the difference here, there's a difference from this original one. What was the rank of this matrix? That original one? 2, right? It was healthy. It's got the full thing. the rank of this one, manifestly 1, right? So this is a multiple. Yeah? So rank m equals n equals 2, rank r equals 1. So in terms of this singular value structure, we're only going to get out a first piece because the next singular value has to be 0. Singular values 0 correspond to null space vectors. All right. So let's try it. So if we did this, so the procedure again is to find e values. These are the sigma squareds, and e vectors. These are the v's of A transpose A. That's how we do it. Someone says do SVD. Start off with this. So see if you can write that down. A transpose A. 3 minus 1, 3 minus 1. 3 minus 1, 3 minus 1. Nope. It's A transpose A, not AA transpose. Solve, solve. All right, so we're going to get 18. Tell me when I get it wrong. So we're going to minus 3, there's a minus 6. What will be here? For sure. Without doing any calculations. It's minus 6. This is a symmetric matrix always. Right? So minus 6, and indeed it is minus 3, minus 3. Good. Minus minus these guys, so we'll end up with a 2. It's symmetric. So that's why all the good things come out. We know that symmetric matrix, it's real and symmetric. It's going to have real eigenvalues. It's going to have eigenvectors that are orthogonal to each other. Awesomeness. Okay? Yes. So you go and compute these things. So find the lambda. Find e values. Let's do it, because this is what we do in this class. Okay, so we'd have A transpose A minus lambda times the identity. We have to set this equal to 0. Give me some chalk. Okay. Okay, we're doing it. So this is good. And this is going to be this thing. So 18 minus lambda, right? You just subtract them off the diagonals. Minus 6, 2 minus lambda. Write the whole thing out. So we're going to have 18 minus lambda, 2 minus lambda. This is where we always go wrong, right? There's minus 6 times minus 6 with a minus sign. It's very easy to flip that one. Yes, this was correct. This was bad. Yes. Thank you. Damn it. All right. Okay, people. Okay. Form is off. Okay, so let's see. So 36. Minus 20 lambda plus lambda squared, and then amazingly we have minus 36. So why would that work? We should actually expect that. So there's 36, they cancel. So, and this is lambda squared here. So we've got lambda, and it looks like lambda minus 20. Right, so we can say lambda 1 equals 20, and lambda 2 equals zilch, right? Zilch. A nice easy place to make a mistake here is not getting the squareds right. So sigma, we've ordered them in size. They were always going to be positive because we showed that this is a positive definite matrix. So this is a PDM. Actually, it's a semi-positive definite matrix. So we'll know we'll always get eigenvalues that are greater than or equal to 0, and we can order them. So we should do that. Lambda 1 will be 20, lambda 2 is 0. So lambda, so sigma 1, so that's 20. So sigma 1 is the square root of 20, 2 root 5. And sigma 2 squared equals lambda 2 equals 0. So we've got these characters, sigma 2 equals 0. So our sigma matrix is going to look like this. And I'm just giving you this extra example because it adds some goodness. That's it, right? Here's the rank. Rank R equals 1, sigma 1. So that's all this matrix is. And then if you go through and find the eigenvectors, so insert suffering, minor suffering. You can do this at home when you're feeling like you need some. We would find, just to get through this, we'll find that V1, you have to make it normalize. It's root 10, 3 minus 1. And V2, the little hat, is 1 over root 10. It's going to look a bit like this one. 1, 3, yeah, so 1, 3. So we can see straight away these guys are V orthogonal to each other. Check, we expect that, right? Take the dot product, zilch. So our V matrix, so V is 1 over root 10, and then we're going to put 3 minus 1, 1, 3, right? So V1 hat is here with the root 10, and V2 hat here. 2 ways to find the U vectors. Just to remind you, so we're going to do it the easy way. 2 ways to find the U vectors, the UIs. So we can solve A transpose, which is a lot of work for E vectors and E values and E vectors. It will actually give you the sigmas again. So that's 1. And 2, easier, if you trust what you've done, is that the UI have to equal 1 over sigma I times AVI, like this, right? This is the singular value equation. That thing at the top there, right? That's the fundamental thing we're doing. So if we compute A times VI and divide by the singular value. Great question. All right, so let's deal with that, because that's what's happening here. So if you have a much larger one and you really want all those U's, then you kind of have to do a good job of computing them. Right. Right. On the other hand, once you have that anchoring of the good U's, right, the ones that are going to be used, then you can build out the other set using other ways, like QR decomposition, actually. Yeah. Good. So the thing is, of course, those U's are left null space. Can't go there, right? No one knows what they are. Well, we do, but we sort of ignore, right? So they're off sort of here, but they're attached to sigmas that are 0, so you don't need them. A doesn't get there. Yeah. The Dunning-Kruger of linear algebra. All right, so we've got this. So it's easier to do this. All right. SKP. All right, so okay, so we can do that. Okay, so we can. Excellent question. So it works if for sigma I greater than equal to 0, greater than 0. So the first one would be, we'll do it. All right, let's do it. Where's our A? So we've got 1 divided by 2 root 5. This is going to be for U. So this will be U1 hat equals this. There's our sigma on the bottom. Our A is 3 minus 1. 3 minus 1. The excitement builds. We have 1. What is that thing? What is V? It's this one. 1 over root 10. It's kind of always charming that this works out, I have to say. 3 minus 1. So let's multiply it out. So we're going to have these little bananas out here. Let's get those factors out the front. There's a root 5 there and 1 over and a root 10. So 3 times minus 1, what do we get there? 9 plus 1 is 10. And a 9 plus 1 is 10. And we'll clean things up a little bit. This is, of course, root 2 times root 5. Right, so that root 5 times that character. So we're going to mess around a little bit. This is 1 over 2 root 2. That one goes there, that one goes there. And then there's a 5th. And we had 10 and 10. So they can divide through, so we'll get, okay, this is 10, 10, 10. Okay, good. So 1 over root 2, 1, 1, which is a unit vector. I mean, we know this is going to work. We've derived this. We know this is going to work, but it's always a little surprising. Right? The sigmas have been worked out such that they do the normalization the right way. It's still a bit odd that it feels a little strange. It should feel like magic. It's total magic. Okay, so that's one of them. The other one, the U2, we don't know about. We can just, because it's so simple, we can just figure it out, right? We can just make one up. Because we're never going to get to it. We want to describe the whole space, so that's good. I need these because I mess things up. Okay. So it's a simple matrix, right? It's just a 2 by 2. So we can see U2 equals, let's just choose one, right? So 1 over root 2, say minus 1, 1. Minus 1, 1 works. Okay, but this guy is this is the basis vector for the unreachable, but chartable, I guess, unreachable left null space. A can't make anything in this direction, right? And if you look at A, what's A got? It's got these 2 column vectors, which are just multiples of 1, 1. A times x can only be a multiple of 1, 1, which is this business here. A can't make anything that's off that direction. So let's write down A, and then we'll draw that picture again for this one. Yes, yes. Stop it. I think we're getting close, so great. A equals 3 minus 1, 3 minus 1, pulling it all apart, 1 over root 2, so here's our U1 there, and we made up this one, so it's minus 1, 1, so this is U1, U2, whoops, and then square root of 20 was in here, 0, 0, 0, so A is really just, it's kind of this number here, with some rotations and things. So then there is a 1 over root 10. And this is V transpose. So V is here, 3 minus 1, 1, 3, so we're going to flip that. 3 minus 1, 1, 3, so this is V transpose. This is U, this is sigma. And so this is because this is rank equals 1. Right. Okay, so let's draw a little picture of that. And then I think that will be good. The rest I can just show you on slides, I think. Okay, so is that attached? Yes. Yes, okay. Huh. I'm sorry, poor blackboard. Okay. Okay, so the picture would be this. Okay, let's do it. Boom. Wow. So this is for A equals minus 3. What did I call it? Is it 3 minus 1? Yeah, 3 minus 1. 3 minus 1, right. And we have, I know I've lost the right board here. So, okay, 1 and 3, so it's up like this. So again, we have our unit circle. We're doing okay? Am I making up lies? This is going to be 1 and 3, so it's roughly like this. This is V1 equals 1 root 10. No, that's not right. That's V2. V2 is going to be there. V1 is here. Yes. This So it's a bit funny, a funny looking thing. So V1 is here, it's 1 over root 10, and it was 3 minus 1. 3 minus 1, and this is 1, 3. Yes. Okay, this is R2, which in general is Rn. It's where x lives. And this is y equals a times x. Y equals a times x. What are the mechanics of it? Okay, so over here, we'd have what would be r squared. It's r squared again, but it's rm in general. That's what I'll do. All right, and so we have another unit circle over here. Maybe I'm drawing this badly because it's going to end up in a funny place, but anyway, okay. So we've got 1, this is our good U1, right? U1 is the good one. And then we've made U2 over here, right angles as usual. Good. This is 1 over root 2. So suspicious. And then this is 1 over root 2. And this is minus 1, 1. So what happens is a times this character goes to here. And it's, what is it again? It's 4 times root 5. Is that right? Yeah. So this is not to scale. All right, fine. Let's just draw it here. So this is this is root 20 times U1, not to scale. So what happens is this one gets mapped up to here. This is A times V1 equals sigma 1 times V2, times U2, U1. Oh, it's hard. It's hard. And this is really, in this case, it's root 20 times 1 over root 2, 1, 1. And this is A times 1 over root 10, 3 minus 1. That's what it's doing. And then this gets sent to 0. This is A times V2 equals zilch. So this is null space. This is row space, which we call row space like this. It's a column space of A transpose. This is the unbuildable stuff. This is the left null space. And this is row space, column space, column space. Column space of A. We could draw this picture before because, when we try to find a basis vector for these things, they're one-dimensional. You can't mess this up, right? They're one-dimensional. Our methods for finding basis vectors for column space and row space, etc., were they're okay, but they didn't give us these beautiful things. And it turns out there are these special orthogonal bases for every row space, column space, null space, and left null space. All right. I think that's pretty good. So what's happening here is this is a squish. So it takes all of this, right, and it squishes it into here. Right, so A, if you like, times a pizza equals this thing. Squish. Put in quotes so no one comes to arrest me. This is a squish, right? And there was an axis to it, which is this way. So if you like, I could put an arrow here, and that's how it ends up. That arrow gets mapped to that. And so in general, we have A times a disk, which you can have of any size, A times a disk, equals some crazy ellipse. And let's make it an ellipsoid. All right, fine. Let's make it a ball. That's fun. Make it a ball. Okay, so this is a sphere in Rn. This is an ellipsoid, a hyperfootball ellipsoid in Rm. And there are, I should say this too, it's an R dimensional, R is rank, right? It doesn't matter what, and this is an R dimensional ellipsoid. And there'll be some axes here, right? Nice axes. And it will have taken these and stretched them and flipped them and all sorts of things. You might have to turn this football inside out, or this thing inside out. But that's really what matrix multiplication does. I like it. I'm going to say, all right, so any questions about this madness? So you need to be able to do it, of course, and kind of build it from both ways. If someone gave you this story, they said, oh, it sends these vectors to these vectors with these singular values, you should be able to build this thing and then make a matrix, which is useful, which, if you think about it, is how people construct them for lectures. At least that's how I do it. Okay, so I'll show you I'll give you the summary, the fundamental theorem of linear algebra, because we've added this one piece. We had the whole story, column space, row space, null space, and left null space. But now we have this extra thing that there is this beautiful extra part where we have these orthonormal bases that describe those spaces perfectly. Okay, good. All right, and then we'll have a little game at the end. All right, we'll have a game at the end, and then you can run away. Let's, it's on. I need to do this. Maybe do this. You were feeling sleepy. All right. This is truly the best part of the course, just so you know. All right. Okay. All right. Let's see. The problem is I can't see, can I? Neither can you. All right. I think it was this. Does that work? Okay. All right. I need to point at things. I can't. Okay, so with these characters involved. So this is just going to be a summary. You can print this out. It's just 2 pages. It's not this stuff. There's a little summary version of it. So this is a fundamental theorem of linear algebra. This is what we have now. Any n by n matrix, right? We showed we could do various things for square ones, and sometimes we could do LU decomposition, but we need row permutations and all sorts of things. Okay. Okay, so there's a symmetric story in that A maps this way and A transpose maps this way, right? So you have that same, right? So A's, and that's built into when we say this sort of thing, right? So when we say, we don't say, and this is a good question early on, right? What do we call this thing? Well, we realize that because of the symmetry, we're going to call it the column space of A transpose, which is the row space of A, and the row space of A transpose is the column space of A. So there's this. Right? All right. Let's point at things. Okay, so we have these two. So X lives where we have these 2 pieces that we pulled them apart. There's row space and null space. This is in Rn. B, where we try Ax equals B. This is all about Ax equals B. We have column space and left null space, right? And they have that nice symmetry. And early on, we showed that the dimensions of these 2 things add together. And the dimension of column space and row space are both R, the rank of the matrix, which is kind of a spectacular result. And it's back here. Rank is such a big deal. And then we had this orthogonal complement story, that if you take the basis for column space and the basis for left null space, combine them, you've got a basis for all of Rm for Mercury. And if you take a basis for row space, and we'll get to the right basis, a basis for row space and a basis for null space, and combine them, we get a basis for Rn, where n is Neptune. All right. I know, so look at this. And then here's the picture version, which I know is a lot of suffering involved. Maybe I'll do this. Okay, this is the abstract one. Yes. It's a good thing to know about. Right. Something squeaky. Okay, so, so what we can do, so A times any vector will end up in column space, or 0 is in column space as well. We can always solve these problems, Ax equals P, if P is in column space. And in general, if B is not in column space, then we have the normal equations. We know we can trim off this bit. The bit we can at least we can describe it because we're in, right? It's not the unknown unknowns. It's the known unmakables. And we can trim that bit off and then solve this problem. So that's our approximation story. And that's what we end up with. X star is our best solution to AX equals B. That's our best solution. And we have this story, every point in row space every time we have a solution, we can always just add a point in a vector in null space. And so we'll have infinitely many solutions if there's a nice null space. We have a possibility of no solution if there's a left null space. So you need to know all that story. All right, that's good. And now this is a bit we've had in the last 2 lectures. I mean, it's one part of SVD, but it's a nice thing. So there are 4 fundamental subspaces, and they have this natural, beautiful orthonormal basis for them that we should always find, right? So we have ways of finding them, but this is the way to get them. The V span Rn, it looks a bit funny because when we write this out, we want U, this is what happened, you see. U sigma V, UV feels good, except the V's are here and the U's are here, right? This is left null space because it's an algebra thing, but on the board, it's in the wrong spot. All right, just have to concentrate about that, on that. So we have all these things. We've talked about these bases, these parts of these bases span row space, column space, null space, and so on. And this is the basic story, how A works, right? So A will take one of these singular vectors in Rn, send it to a singular vector in Rm, and multiply with this growth or sort of shrink factor that has to be greater than 0. We have the matrix version, blah, blah, blah. Yeah, okay. And A is just fine. This is beautiful diagonal structure, right? This sigma is always the same shape as A. This is an M by M. This is an M by N because they're just transformation matrices. And sigma is really what A is. Okay, good. I think that's good. And so this is a way you could change this picture, right? So instead of just having kind of random things, the sort of ends of the vectors are right? There's V1, I can't point. There's V1 through VR. You can imagine there's a whole bunch of these here. And then the rest of them describe null space. And the U1 through UR describe column space, and they all match up with each other. Fundamental story is this equation. All right, so I'm going to give you a couple of examples. This is a different thing. This is not on the exam, just for fun. All right, so here's an idea. So we've got a knowledge network, so think of the web, right? So the web, appears in '92. People start linking to things and making these, this whole hypertext business is very exciting. And so so search was a big problem. So the first search engines before you were born were things called Excite and Lycos and so on, and they were, they sort of worked, but they were terrible, right? The way to game them, if you wanted people to come to your site because they were searching for fish, was to put the word fish 1,000,000 times, right? It was very simple. So there was nothing about the socialness or the interaction with other websites in there. And they all got crushed when Google appeared with this tiny little thing on one screen. And I remember actually a friend of mine coming into my office and saying, "Here, try this thing," like whenever it was, 96 or something. And it just found things. It was amazing. Okay, so we're going to say that think of web pages, so that, and the Wikipedia is a good example now. So these pages can have 2 broad aspects, right? So they can be authorities, so they actually have content. So a Wikipedia page is a good example. But they can also have this, hubtasticness, right? So the idea is they're hubs. They're pointing out to other places that are authorities, which, again, a Wikipedia page does both of these, right? So pages could just be authorities. You could just write about something and not point out to anyone. They could just be hubs, right? Say, go here, go here, go here. So John Kleinberg, who's a champion, he's a MacArthur genius, a very nice guy. He's at Cornell, did this work. It was kind of classic Raiders of the Lost Ark sort of story because he did it at IBM and they said, "That's very nice," and sort of put in a box and we'll put our top people on it. You've never seen this movie. And anyway, so he kind of had the idea that other people did it at the same time, and one of them was the Google people. All right. So the best hubs will point to the best authorities, and this is about a particular topic, which is, again, there's a complication there, right? Because you can be authority on fish, but nothing else. So you have to think about that. Let's see how SVD comes out. It's just a couple of slides. So the idea is that good hubs will point to other good hubs and so on, so on, so on, right? So let's just jump through it. So there was a hyperlink-induced topic search.
Okay, we're going to do a slow clap for linear algebra. Here we go.
Why are you here? It's good, man. It's good. Yeah. Thank you. Thank you. God, I don't pay him enough money. All right. We love linear algebra. Okay. He should be teaching too. So we're going to do this exciting thing. We'll give each node 2 scores. So we're going to put a little number next to each one of them. Suspiciously, we'll call them X and Y. So one will be how good it is as an authority, how good it is as a hub, right? How much it points, and think about fish. And then we'll connect them if they're connected in a network, right? So if you're a good hub, you'll point to good authorities. And so you can do this with all sorts of things. Supreme Court decisions. People use PageRank to study, all crazy things like food webs, all sorts of stuff. And networks are everywhere, right? There's a big, big story. They've always been everywhere, but we just got to the data story in around 2000, and everyone's like, oh, they are important. So a good authority is linked to by good hubs, and we could write it like this. So X should increase as this number increases. So that AJI is, it's like our A matrix, but it's, here we're just going to have ones or zeros. So a 1 means that J points to I, right? So you'll call these things adjacency matrices, and you'll have them in graph theory and so on. So that's just a 1 or a 0. So if the more that Y points, these node J's, right, these J nodes point to I, and if they have good hub scores, then it has a good authority. That's the idea. Okay, so it's a direct link. And then we have the other thing, that good hubs will point to good authorities. So that will be the other way around. So your hub score should go up as a function of something like this, right? So it's a sum over Aij xj, and Aij is 1 if I points to j. Right? So if you point to a whole bunch of things that have really high x scores, then you'll have a higher y score. You'll have a higher hub score. If they have good authority scores, you'll have a better thing. It's a linear, there's a lot of assumptions in this, but it's not bad. So if you play around with that, you can see that these are actual products, right? That second one, I'm pointing into space. This second one, this is really just the matrix operation A times X. And this one is, because the J and the I are flipped, is A transpose Y. So we can say that X is proportional to A transpose Y, and Y is proportional to A times X. And then you can put them together, right? Stick them together, and you get, blah, blah, blah. Yeah, this bit, right? Here it is. So X recursively is going to be A transpose A times X, where the A encodes the network structure. 1s and 0s, that's all. And Y will be AA transpose. And that's the matrix that we see, that structures we see over and over again, and it's the singular value decomposition stories right there. So singular values are behind the original Google search structure, which is strange. And you can also play around with this and set little random walkers running around. Just do this theoretically, let them run around your network, and where they kind of lump together, there's another thing here, but where they lump together, you can say rough. That's kind of what they did actually, because it's a very large matrix to solve, too hard. So we got all these good things, right? Symmetric, semi-positive definite, you know about these. There are some other things. These are all these things you just list straight away. There's the Perron-Frobenius theorem, which you don't know about, but that's a cool thing too, which says that there's one eigenvalue that's bigger than all the others. So there's a winner, which is good. Anyway, so that's kind of cool. Okay, so let's do one last thing. I mean, that's amazing, right? Now, Google's changed a lot. I mean, it's not what it used to be, because they've got all these little, now it's much more of a contraption. It's much more biological and weird, and it's got all these little things that do things. Okay. Exceptions and so on, and it's not as good as it was in a lot of ways. Okay, but I should also say, so it was much harder to game Google, because you had to build a whole farm of web pages that were pointing to each other and so on, right? You couldn't just load fish into your metadata. So that was harder. Of course, people are smart. All right. So gaming Google was a big deal. Of course, don't make a good quality product. Just try and trick people, which is something we talk a lot about in my other courses. Okay, let's see. So being good people. let's see. So let's do something completely different. Now we're going to say, this is not about a matrix multiplying anything anymore. All the photos that you take all the time are matrices, right? They didn't used to be, but now we've got them on phones. They're all matrices, right? JPEGs, PNGs, they're all matrices. And in particular with something like, so if you've got color, right, then there are 3 matrices. There are 3 matrices, and you stack them together, and you look at them, and you think, that's terrific. Show me more slides from your holidays. Okay. So what we'll do is say, well, let's approximate them. So there's a lot of work that goes into finding minimal representations of systems of all kinds. And so we'll do it for images, just for fun. So we have this nice fact that these sigma values are all ordered by choice. And what we can do, if I have this slide again, this board, that's what I was saying before is, right here is this thing, we can just chop it somewhere. And in fact, we could just do it like this. Let's take the best approximation, or the one with the highest sigma value, look at that one, then look at this, then add this one, then add this one, then add this one. So we'll do that and see if you can tell what the pictures are. Because they're outer products, everything you add will be a piece of tartan. Somehow you can make circles out of that, right? All right, so the rank R has to be, so we know this for rectangular matrices, the rank has to be, it can at most be the length of the shortest side of your photo. It might be smaller if it's less complicated. Right, if it was just all white, then the rank would be 1, right? It's just a stack of white lines. And so we're going to do something a bit different because instead of having just this one piece, say we have RGB, right? Red, green, blue. We'll have those 3 matrices and we'd have to do an SVD for each one. And then we'll stack them together. So you'll get a bit of extra information when they're colored actually because, right, we're not just adding 1 matrix at a time. We're adding 3 colors at a time. All right, so we're going to do this, and this will be the end of the course. We'll see how you go. See how I go. Okay, to start with, let's actually do tartan, right? So this is of the MacLeod clan. For Highlander fans out there, you'll be, no, Highlander? Great, great, terrible 1980s movie. Right, there can be only one. All right, for some reason, Sean Connery's in there. Anyway, we have a Frenchman playing a Scot. It's fantastic. Okay, so this is, what's going to happen with all these figures is the bit on the right will be the piece that's being added now, right? So if we've superposed 30 of them, then the bit on the right will be 31 adding it on. And you're going to see that there's not much that we add after a while, right? The first one is really a big piece, and the next bit will look black most of the time. So this is a grayscale version of the MacLeod tartan. And so it's just simple. So that's the first outer product, right? That's this piece. It gives you, obviously it looks like tartan, right? It's pretty good. So we're going to have one more bit. Of course, within this, you see the pictures of the fabric, right? It actually has a weave this way as well. That's a diagonal, so you've got to create that. So that's one. All we're adding is that what seemingly black piece over here that's using the same color scale. But you can see now, I'll go back to the first one. We've added a bit, and now there's a little bit of texture in there, right? Not much. And this is the most ridiculous example you can use because, and so you can start to see some of the weave of the fabric is in there, okay? All right, and you start to see the fabric. So that's 4, and this is out of 640 matrices that we can add together, right? So what you see is after about, so I'm going to go to, that's 10, you can actually see the fabric now, and you don't get much more, right? We won't improve on this much more. So it's going to jump to 100. So going from 10 to 100, it's a bit better, but it's not that much better, right? And then we'll jump to 300. So most of these things don't count, right? So these sigma values are decaying, and most of them don't count. Does this make sense? It's exciting. I'm thrilled. Okay, and that's 640. So that's everything there, right? And we're basically what looks like, adding nothing every time, but it's improving. All right, so I'll give you a few others. The next one will be the actual color. So this is the real color, and so now we've got these 3 matrices. Each one has a singular value decomposition. We're going to add each one at each time. So there's a bit of extra information. So you see how that fills in a little bit. Again, that same kind of thing. Okay, that's 10, 100. So for between 10 and 100, you get a little texture, but that's it. 300, 640. Okay, so here's the first, it is 3 colors, so it is 3 matrices added together. It's not just one. If we just did it with one, it would be harder, I think. So what's this? It's an excellent answer. It's a good question, yeah? It could be, it really could be, yeah. It's another important vehicle of sorts. All right, I'll add one more. Any big guesses? That was a really great guess for a lot of reasons. So I watched Doctor Who as a kid, and it terrified me. You know, and it was terrible as well. So that's all that's been added, right? This piece has been added. Oh my God, we're running out of time. All right. That's 3 out of 540. What is it? It's the Earth. All right, you're standing on it. Yeah. So it's 4, 5, 6, 7, 8, 9, 10. And then we're going to jump. That'll be 20, 30. So after 40 out of 540 of these simple outer product matrices, it starts to fill in. There you go. All right, 1. Did we do this? Ah, you've seen it. Oh my God. All right. I think I showed you at the start, didn't I? But still, you're right. So that's just two of these pieces of tartan, and we've got eyeballs, and now you've got a moustache with 3. All right, now I have a batch more to show you, and then we'll be good. So this is how these singular values look. So the first one, of which you guessed immediately, right, has an enormous number, and then it decays. All right, what's this? You're not going to get these. So that's 2 pieces, 3, 4, 5, 6. Who are these people? These are my people's people. Just wait on, I have more to show you. Just wait. Okay, fills right in. What about this one? All right, we'll do these quickly. This one. So this is, okay, look at this. So this has got to have, it's tilted a little bit because of my terrible drawing, but it's tilted a little bit, and it's going to get it. It's going to make it, go off, right? This is writing. So it's Zork. I just have a few more minutes, I'm going to show you. So that writing is harder, right? And then we're going to put this, so 2, there you go, eyeballs after 2. Cubit. Right, what about this one? No, this is not any of it. This is a different set of things. That's 3. All right, Darth Vader, good. With geek in the background. So this is 1. This is Brutus. Brutus is a sea turtle on the north shore of Honolulu. He was found on the Ides of March, so that's why he's there. This is off the island of Salina, which is near Lipari, which is an unbelievable part of the world north of Sicily. That's the owner of Lammy, the Lammy and Sealy. That's the owner of Lammy walking there. Lipari, it's just unbelievable place, ridiculous. This is a moped. I'll show you just a few more. Okay, what's this? Tree, that's a tree. Colosseum, good, yep. Bicycle, yep, right, excellent. That's in Oxford. The English, absolutely hopeless human beings. This is in Seoul, in Korea. This is a beautiful temple. It's a reflection in the water. I like to take photos. This is really what it looked like. It's unbelievable. Nearly finished, people. And then you can run away. These are temples in Kyoto. This is like 5 miles of this, where you can rejoice that you're alive, of climbing and climbing through these things. This is Oh, Nantucket. This is in Kotu, which is off the north part. Beautiful. Ridiculous. That is a seashell. And this is the last one. So this is... So the approximation's on the bottom of the bit. It's another planet of sorts. So this is Lake Champlain, which is fun to run on when it gets cold enough. All right. Okay, thank you. You've been great. Look to the website for updates, things. Come back here on Monday. Bye-bye. Thank you, team.